Okay, if you look in the uh, course materials, in the materials for Unit 5 for this week, week of 1-4 to 1-8, I added two more things. One of them says more hydrocarbons practice, and then there's this honors chemistry, hydrocarbons, and acid practice. So this is in the assignment list as well, and it's like a quick check, like a homework thing for that you need to complete by tomorrow. And you can do it today if you want. You should be able to do it. So, um, oops, hold on. Oh yeah, it should only show up one time for you, where it says honors chemistry, hydrocarbons, and acid practice. So it's a mix of problems that deal with acids, which we kind of did like on Monday and Tuesday and whatnot, and these hydrocarbons, both straight chain and um, cyclical or ring hydrocarbons. So that should be in your upcoming, and you can complete that by tomorrow. But in the materials section, there are the problems which I asked you to try for today, and I'll go over those with you now, and then I'll give you some time to like work like in like during class time, and we'll all just kind of stay in the room together, and I'll just kind of like let you work on it for whatever, maybe 15 minutes or so, and then we'll go over them. So what I'm talking about here is, and this should help you, the hydrocarbons practice 2. I'm going to go over those right now with you, and then the more hydrocarbons practice, this is what I want you to try while we're here together in the room, and I'll answer any questions you have about anything that you need to know about naming acids or hydrocarbons or whatever, and then you do the hydrocarbons and acid practice. So anyway, in the hydrocarbons practice 2, there were a mix of kind of different things to do. There's both form or structures that are shown, and those structures uh, show you the number of hydrogens and carbons that are in the individual compounds. And oftentimes we write the hydrogens and the carbons, but this one here is just that like bent or stick model, and wanted you to write both the formula and the name. So this is space for the name and the formula. And then there were problems that I wanted you to draw the structural diagrams. So you can include the condensed diagram, but I'm going to show it to you a couple different ways. And this one here, you shouldn't draw a line diagram because it kind of doesn't make a whole lot of sense. And it's important to see like the number of hydrogens. The ones that are the more hydrocarbons practice, the ones that we'll do today together, or like give you some time and then we'll go over them. This one here. So some of them even like this might look like it's nothing, but that box is a meaningful thing. There's a carbon in each of the corners, and you can figure out how many hydrogens there ought to be too. And I'll show you how to do that. And then there's some structural diagrams that you can draw for each of those individual compounds. Okay, let me change to a different screen here. Go to this one. All right. So in the that homework 2, let me see if I can change the size of this real quick. Turns out I can't use the whole screen. I can't write down at the bottom of the screen. It does a wacky thing. I don't know if I've shown you this, but if I draw here, it's all good. When I go down here, it does that, which is pretty insane. And it works sometimes, and other times it doesn't work. I don't know why that happens. It's a total nightmare. But I still get like probably 90% of the screen I can write on. Okay, so number 1, if you want to know the formula for the compound, all you got to do is count up the number of carbons and hydrogens, and you always write the carbons first. So there's 1, 2, 3, 4, 5, 6, 7. So there's 7 carbons, C7, and then it turns out that there's 7 carbons on the top, 7 on the bottom. That's 14, and 2 more is 16. C7H16. They're all single bonds, so it's an alkane. So you want a 7-membered carbon that's an alkane. That's heptane. That's it. There's no double bonds. There's no triple bonds. There's no rings. But we're not doing anything with groups off the side of it. They're all just single bonds. That makes it an alkane. And you know, the rule for alkanes is it's like CX and then H 2x plus 2. And this follows that rule that if the value x is 7, if you were to put a 7 in here, 2 times 7 is 14, plus 2 is 16. So that follows the rule for alkanes too, is like a double check. All right, so the number 2, there's 2 carbons. So that's C2, and there's 4 hydrogens. That's H4. And so it's got to have a name for 2 carbons, which is F, and then there's a double bond. So that makes it an alkene. So it has to end with ene. And so you got F, ene. F meaning 2, ene meaning that it's an alkene. And the rule for alkenes is that it's CXH2X. So here, there's 2 carbons. So if you have 2 carbons, and if you put a 2 in here for this X, 2 times 2 is 4, C2H4. So that equation works out correct, and it's named as an alkene ending with ene. All right, so then number 3, there are 4 carbons, and they form this ring. So you got 1, 2, 3, 4. So it's C4, and then there's the hydrogens are indicated as how many hydrogens are with each carbon. So there's 2 hydrogens here, 2 hydrogens there, hydrogen down here, and hydrogen here. So that's 6. C4H6. So there's 4 things in a ring, and because it's a ring, the rings have the name cyclo, and then the number, and then it ends with whether it's an alkane, alkene, or alkyne. And in this case, because there's a double bond, it's going to end with ene. If they were all single bonds, it would end with ane. If you saw a triple bond, it would end with ine. So because it's a ring, it's cyclo, and then 4 is Butte. So it's cyclobutene. Now, here's an issue that plagues us in chemistry, and it's why we have to have names and formulas together for particular compounds. And it goes like this. If you look at C4H6, that also follows the formula for an alkyne. So this is an aside, but it's an important aside. There is a formula, or there is a compound, C4H6, and I'll show you. I can do 4 carbons, and then put a triple bond here, and have some hydrogens, filling in all the rest of the spaces that would be in the Lewis structure, like that. I've got 4 carbons, there's 6 hydrogens, there's this triple bond, there's C4H6, and that is butane. So you can have 2 different compounds with the same number of carbons and hydrogens, but with a completely different structure. And that's a very common thing in organic chemistry. So if you just have a chemical formula, it's oftentimes not that useful. In other words, if I say, oh, I got this compound C4H6, well, which one are you talking about? Are you talking about butane, where the 4 carbons are all in a row, with the 6 hydrogens filling in the excess spaces so that every carbon's got 4 lines coming off? Or are you talking about cyclobutane, which has a completely different structure? It has a different melting point, has a different boiling point, it has a different chemical reactivity. You can, in other words, different groups can be added to it. It's just a completely different chemical altogether, even though it's made of the same numbers of carbons and hydrogens. So that's why we have to have names and formulas going together so that you know which one you're talking about. All right. It's not as if the formula itself tells you everything about the compound. The name tells you more than the formula, and the names have to go with the formulas to get you something complete. All right, in number 4, there's 1, 2, 3, 4, 5 carbons. So it's C5, Oops, I don't really want that in red. Doesn't really matter though. Well, that didn't work. Let's try that one more time. There we go. C5, and then count the hydrogens. There's 5 on the top, and 6, 7, 8, 9, 10. C5H10. So that follows the same formula as an alkene. And alkenes, the number of hydrogens is exactly double the number of carbons, and C5H10 works out okay for an alkene. And alkenes have double bonds. And you can see here, there's a double bond. But the double bond is not on the end carbon. It's not on carbon number 1. When you number these carbons, you can number them from left to right, number them like 1, 2, 3, 4, 5. Because the double bond starts on carbon 2, we have to include a number 2, and then there are 5 carbons, so 5 is pent, and it's an ene, 2-pentene. That you have the 2 tells you that the double bond starts on carbon 2. If it were just pentene by itself, like just the name pentene, it just goes like this. And then there's, let's see, you gotta have a hydrogen here, there's one here, there's hydrogens everywhere. Stacks on deck of hydrogens. 5, 6, 7, 8, let's see, I gotta have 2 more on here, 9, 10, there we go. So this is just regular pentene. You don't write 1-pentene or anything like that. If the double bond is on this carbon, or if it's on that carbon, carbon number 1, it's not necessary to write the 1. But because the double bond is in here on the second carbon, it's got to be 2-pentene. So again, same formula, but different structure, and then different names. So different names go with the different structures. Okay, then number 5, that's an example of a simplified model of or an organic compound. You've got these 3 lines, and there's a single line and then like a double line. Every time there's an end of a line or a kink in a line, that's the presence of a carbon atom. So the backbone of this compound is there's a carbon atom, single bonded to a carbon atom, and then double bonded to another carbon atom. So looking at just the backbone, there's a carbon that's here and here and here. So there's 3 carbons. Actually, I'm just going to slide this over, put it over here. So the carbon, carbon, double bonded to a carbon. And then there have to be hydrogens. And the deal with those hydrogens are every carbon atom's got to have 4 lines coming off of it, representing the 4 valence electrons that the carbon itself needs. So starting with this carbon over here, there's only 1 line. This represents 1 carbon or 1 electron that carbon's contributed to a single bond. So there's got to be a hydrogen here, hydrogen here, hydrogen here. This carbon, there's 3 lines coming off of it. So I need 1 more for a single hydrogen. And down here, this carbon's got 2 lines coming off of it. So I need 2 hydrogens. So you satisfied the octet rules for the carbons. Every carbon has 4 lines coming off of it. Each line represents 1 of the valence electrons that carbon contributes to the bonds. It's got 4 lines coming off this one, 4 lines coming off this one, 4 lines coming off this one. Like sometimes students are like, well, how many lines do you know how to do? Or how many hydrogens are there? Well, if your structure just looks like this, where we've got carbon and there's 3 lines that come off it with a single hydrogen, that's not enough lines. I need 1 more for 1 more hydrogen. So it turns out that there are 3 carbons, C3, and then the number of hydrogens. You can't tell the number of hydrogens from the diagram the way that it's drawn. You've got to expand the diagram and figure out how many more hydrogens have to be there so that you have 4 lines coming off each carbon. So I got 1, 2, 3, 4, 5, 6, C3H6. So that follows the formula for an alkene. An alkene's 3 carbons, and then 3 times 2 gives you 6 hydrogens. So it is an alkene. An alkene means there's a double bond, and in fact there is a double bond. And because there's 3 carbons, it's propene. So it turns out that of these problems, there were no alkynes. And although 4 of them end with ene, it doesn't necessarily mean that they're all straight, because the cyclobutane is a ring. But it does have a double bond because it does end with ene because there is a double bond. It's an alkene. All right, what kind of questions or confusion do you have about any of those or the way the names go? And the formulas have to be perfect. The names have to be perfect. You can't have one letter wrong. You put a wrong letter somewhere, it's not okay. You can't just say, oh, ethene and ethane, those are the same thing. It doesn't work that way. It's got to be perfect. Any questions? You put it in the chat. You can like just turn on your mic and holler. All right, let's see. Then here we want to have structural diagrams. And I'll show it to you a couple different ways. But hexine, and there's no number in front of it. So hex means 6, means we've got to have 6 carbons. So you can start out by just drawing 6 carbons all single bonded to each other. But then the end of the name is ine. So that means that it's an alkyne, meaning there's got to be a triple bond somewhere. And because there's no number out in front, that triple bond goes on a carbon on the end. And doesn't matter if you show the triple bond over here or if you show the triple bond on the other end, as long as it's on an end carbon. And then you got to put some hydrogens on them. So every carbon's got to have 4 lines coming off, and the ends of those lines have hydrogens. Hydrogen is the most common element in the universe. Around 99% of the universe is hydrogen. The next most common element is helium. Here on Earth, we just happen to have a large collection of other atoms. Planets are places where hydrogen is not as common and higher mass elements are common. So don't be like, where are all these hydrogens coming from? There's hydrogen everywhere. I mean, water is made of hydrogen and oxygen. 2/3 of every water molecule is a hydrogen atom. There's just hydrogens all over the place. It's not like in this world we're like, man, I wish we had some more hydrogen. There's just hydrogen everywhere. We're never like dying for hydrogen or looking for it. All right, so here I drew that 6 carbon chain, put a triple bond on the end, and here, because these carbons already have 3 lines connecting them, this carbon here, the second carbon, doesn't have any hydrogens coming off it at all because it's triple bonded to this carbon, single bonded to that one. But the carbon on the end, it's triple bonded to the second carbon. It needs one more hydrogen. So that's the way you can draw that formula in one way. You can also write the formula like this. You can write CH with a triple bond, C, CH2, CH2, CH2. Let's see, how many more do I got to do? That's 3 CH2s and then CH3. That's an alternative way. So instead of writing or drawing the bonds and all the hydrogens, it's known that these hydrogens are single bonded to and come off the carbons. So that's an alternative way to write it. Another way, as a condensed diagram or as a line diagram, is to just show the presence of the carbons as the ends of lines. So I got 1, 2, 3, 4, 5, 6, just like that. This is another way to draw that same compound. I've got a carbon would be at the end of these triple bonds. Another carbon is here. That's the second one. 3, 4, 5, and 6. And it's known that there are hydrogens that come off it. So probably from hexine, you could draw this, but then you wouldn't necessarily know what the formula comes out to be. But you can know based upon the generic equation, CXH2X plus 2, that if it's hex, it's C6, and then H, 2 times 6 minus 2, that's not plus, that's minus. Let's see. 2x minus 2. So 2 times 6 is 12 minus 2 is C6H10. So C6H10 is what it ought to come out to be. And when you count up the hydrogens, you got 4 hydrogens on the top, 4 on the bottom, 1 on each of the ends. C6H10 is good. So I did a lot of extra stuff. If you have any of them, this structure here, this is okay, or this is okay, or this is okay, Any of those three is completely okay. All right, 2-butene. Butte is 4. So one thing that you can do is start by drawing 4 carbons in a row, single bonded. But it says butene, which makes it an alkene, and alkenes have a double bond. This number out front tells you where the double bond starts. So in this structure, this is carbon 1, carbon 2, carbon 3, and carbon 4. Or on the second carbon, that's where the double bond is. And it really, you can see here, it doesn't matter if you number from the left or from the right, because the second one in is this carbon, or the second one in happens to be that carbon. So that's 2-butene, but you need to get some hydrogens on there. And for now, it doesn't really matter if you put the hydrogens on the top or the bottom. There's a particular way that it's actually done. For this one, it's actually like appropriate, oops, to put this hydrogen down there because they're usually oppositional because the electron clouds are trying to get away from each other. And then it's like all bent and whatnot. So that's good for 2-butene. You can also write CH3, CH, CH, CH3. And because it's an alkene, the formula for that generically is CXH2X. So it was C4H8. And whenever you count up the number of hydrogens, we got 3 on this carbon and 3 on that carbon, that's 6. And then 2 more is 8. The other way you can draw this structure is like this. Oops. I don't need C's, I guess. Like that. There'd be a carbon here, one here, one here, and one there. So I got 4 carbons, and then it's known where the hydrogens go around it. All right, methane is super easy. Meth means 1, and there's no such thing as methene or methine. It's just carbon like that. That's the only real structural formula that you can draw for methane. Because if you were to write CH3, I'm sorry, CH4, that's kind of like not particularly helpful because it's just the formula for the compound. It doesn't show like where any kind of bonds are. This is sort of an exception though. CH4, that's just the chemical formula. And you can't really draw a structural diagram because if you just draw a single line, that indicates that you've got 2 carbon atoms, 1 on each end of the line. So that's got to be it. All right, 2-pentene. Pent means 5. So we'll start off with 5 carbon atoms. It ends with "-ine", which means that it's an alkyne or has a triple bond. And where the triple bond is on the second carbon. So it's not on this end carbon, but it's got to be the second carbon in. So pent means you got a 5 carbon chain. Ine means there's a triple bond. The 2 tells you that it's on the second carbon. Then you got to throw some hydrogens on here. You just add enough hydrogens so that there are 4 lines coming off of each carbon. And that's good, because now we've got 4 lines coming off this carbon. There's 4 lines coming off this one because there's a triple bond on the left, the right, single bond on the left. Similarly here, triple bond on the left, single bond on the right. Each of these carbons has 4 lines coming off it. So that's one way you can write it. You can also write like this: CH3, C, C, CH2, CH3. If you want to draw it as a condensed structure, 1, 2, 3, 4, 5, and it's on the second one like that. So there's 1, 2, 3, 4, 5 carbons, double bond on the second carbon. This is okay, or if you want to, you can draw it like this and put the double bond over here. Too many lines. Here we go, like this. Either way is all right, because the second carbon would be at this position or at this position, Whether it's on the right or the left doesn't really make any difference. Usually you just draw it on the left, but whatevs. All right, ethene. Eth is 2, so you got 2 carbons. And that it's ene means that there has to be a double bond. So it's a carbon double bonded to another carbon. We need some more hydrogens. So I got hydrogen, 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 hydrogen. So that's good. We don't write, it's kind of a funny one. We don't write ethene as a uh, line structure. And that's because if you were to draw this as a line structure, it would be an equal sign. And talk about, I guess, confusion. You're like, oh, there's an equal sign on my paper. You're like, oh no, that's ethene. Oh, maybe, I guess. It's just confused for something else. All right, so those are answers to the problems from that practice. So here's what I want you to do. Take, let's see how much time we have left. We have like 15 minutes left. Um, I lost my browser. Take the next 10 minutes and work on the in the unit 5 for this week. There's this more hydrocarbons practice, and I'm going to leave it up on the screen anyway. So if you just want to like look at it in the Zoom, that's cool. Or if you want to look at it otherwise, I can't show it all because so much fits on the screen, but I'll leave it on the Zoom. So try these. We're looking for names, and then if you get through those 5, then at the bottom there are structures that you can draw for 6, 7, 8, and 9. So try those for practice like right now. If you have questions, I'll take questions right now too. Just put them in the chat or just turn your mic and just holla. Aubrey, we're just working on the more hydrocarbons practice that's in the folder for this week. I didn't notice if you were in earlier, but just let you back in. It's cool. No problem. All right. So there's only like a minute or two left. Well, not a minute or two, like 5 minutes left. Okay, let me, let's see. Okay, so I wrote some answers on here so we can kind of go through this pretty quick. All right, so the first one thing you can do if it's kind of like crooked and whatnot, which is a totally okay to draw structure, and it's actually quite good to draw the structure of number one this way, is you can kind of like straighten it out so that put the carbons all in a straight row. There's 1, 2, 3, 4, 5 carbons, and there's double bond on the second carbon. So here I've like lined them up in a straight row. That might make it easier for you to see. There's 5 carbons in a row, so it's pent. There's a double bond, so it ends with ene, and the double bond comes off the second carbon, makes it 2-pentene. So I've also appended to this what the meanings are. 2, because there's a double bond on the second carbon. Pent, it's a 5-carbon chain. Ene, that there's a double bond that's present. Number 2 just looks like a box, but that's cyclobutane. Cyclo, in that there's 4 in a ring, or cyclo, that there's a ring. Butte is 4, and that they're all single bonds. They have to be single bonds for cyclobutane. There's just 4 in a row. If you wanted to draw that out, it's carbons like this, and then you got to have enough hydrogens. So there's a bunch of hydrogens coming off here, in case you needed to know what the formula for it is. So that's the theoretical cyclobutane. 3 is really easy. That's methane. 1 carbon is meth, and well, there's no such thing as methane or methane or methane. It's just methane. Number 4, you count the number of carbons in a row. That's the first part. So really the 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 middle of the name, or the most important part of the name, is how many carbons. So you got 6 carbons in a row, so it's hex. There's a double bond, so it has to end with ene because it's an alkene. And where that double bond is on the second carbon. It's not correct to call it 4-hexene, because although you might number the carbons 1, 2, 3, 4, and say, oh, the double bond comes off the 4th carbon, you number them so that the numbers are as low as possible. Start on the left or the right hand side here, so 2-hexene. This is cyclohexene. Cyclo because it's a ring. There's 6 carbons, 1, 2, 3, 4, 5, 6. It's a hexagon, and then there's a double bond. It ends with ene, so that's cyclohexene. It's actually kind of like the same as 2-hexene, but it's kind of like all in a ring. All right, and then the last page, draw the structural diagrams for these hydrocarbons. 2-butene. Butte is 4, so I got 4 carbons in a row, and it's an alkene, so it's got to have a double bond, and that comes off the second carbon. Doesn't matter if you're numbering from the left or from the right, it's the double bond is between the 2 central carbons, and then there's the appropriate number of hydrogens. Cyclopentene, or cyclopentine. So pent is 5, there's 5 carbons in a ring. It ends with ine, so it's an alkyne. It's got to have a triple bond. So you got a triple bond between, it doesn't matter which carbons because it's a ring, so there's no real numbering scheme here. There is a numbering scheme for cyclic or aromatic carbon groups, but it won't be applicable in this course. Here you got a triple bond between any 2 of the carbons, and that satisfies the octet rule for those 2 carbons because there are 4 lines coming off of each of those 2 carbons then. So the only other hydrogens, the hydrogens coming off all the single bonded carbons. But this is another way you can draw it, where it's just the simple line structure. For propine, prop is 3. Ine means that it's an alkyne. It has to have a triple bond. It doesn't make a difference where the triple bond is because there's only 3 carbons. You can either put them on the right or put them on the left. Either way is okay. In other words, you can draw that structure like this. You can be like, oh, I got carbon, carbon, and then hydrogens going like one of these kind of deals. This is exactly the same structure. This is the same as that. It's just a mirror image. This is a way to draw the line structure. And ethane, but draw the structural diagram, is just like this. 2 carbons, and they're single bonded to each other because it ends with an ane. Again, this structure you would not draw as a line diagram because that would just be a single line, and that could easily be confused for something else. The only time the line structure is useful is if it's clearly a chemical. Like you've probably, you don't see this a lot in your life, like some kind of thing like that, where you're like, oh yeah, I know what that is. That's confused for whatever. That's not confusing for anything else to a chemist. That's exactly like, well, that's not the same. That's not this chemical here. That's just a separate example. That's like a totally unique thing. All right. Well, class time's about up. So, do the, what do you call it, by tomorrow, by the end of tomorrow, but I'll tell you about that tomorrow too. So have a good day. Have fun in your next class and whatnot. Keep it real.